basic code and transform it into a highly efficient, reusable, and absolutely crash-proof software architecture. How? By digging into the incredible mechanics of Java inheritance and interfaces. Let's get into it.
You know, just like snapping together interlocking building blocks, great programming is all about connecting perfectly designed pieces. And the ultimate superpower in software development? It's literally never having to write the exact same code twice. That is the true essence of reusability, and it's exactly the capability we're going to unlock for you today.
So here's our roadmap. We'll start with the core concepts and the different types of inheritance. Then we'll hit a massive roadblock known as the diamond problem, introduce the Java interface to solve it, compare classes versus interfaces, and finally, wrap the whole thing up with key rules and keywords. All right, Section 1, Core Concepts of Inheritance. Before we get into any of the really advanced modular designs, we've got to establish the absolute foundation of object-oriented programming.
Basically, inheritance is a mechanism that allows one class, which we'll call the child or subclass, to automatically acquire all the properties and behaviors of another class, known as the parent or superclass. In Java, you actually do this using the extends keyword. It's the absolute cornerstone of Java architecture because it completely eliminates redundant copy-pasted code. Plus, it makes future maintenance incredibly easy. Think about it. If you need to update a core behavior, you just change the parent class, and boom, every single child class inherits that fix instantly. Moving right along to Section 2, Types of Java Inheritance. Now that we know what it is, let's expand this family tree a bit and look at the specific evolutionary paths our code can actually take. Java natively supports single inheritance, which is just one parent to one child. It supports multi-level, branching from parent to child to grandchild. And it even supports hierarchical, where one parent branches out to multiple different children. But there's a catch. Multiple inheritance via parent classes, that is a hard no. We're going to see exactly why that is in just a minute, but first, let's look at one of these actually supported paths in action. This setup brilliantly illustrates the trickle-down effect of multi-level inheritance. Step 1, we've got a base class called animal with a simple eat method. Next, dog extends animal, keeping that eating ability, but adding its own specific bark method. Finally, baby dog inherits from dog. And here's the beauty of it. Without writing a single line of duplicate code, our baby dog organically acquires all the generic traits of an animal, plus the specific traits of a dog, and then adds its very own weep method. Because, let's be honest, that's mostly what puppies do. It's an amazingly logical way to build capabilities. Section 3, the diamond problem. Okay, we've built a great family tree, but we need to bring the momentum to a complete halt right here, because there is a catastrophic conflict lurking in the system that we absolutely have to address.
I really want you to imagine a critical scenario for a second. What happens if a child class tries to inherit from two different parent classes, but both of those parents have a method with the exact same name and the exact same behavior? I mean, whose behavior does the child actually adopt?
Well, the answer is total system-breaking ambiguity. If two parent classes define the exact same method, the whole system crashes because the Java compiler simply cannot determine which version to use. This is what's known as the diamond problem, and it is the exact reason why Java strictly bans multiple inheritance through classes. It's a massive structural vulnerability that could cause huge logic failures. The diamond shape might look pristine conceptually, but in Java class architecture, it's deadly.
So, how do we fix it? That brings us to Section 4. Enter the Java interface. To bypass this massive roadblock and still achieve those complex hybrid software architectures we really want, we need a hero to save our code. And that hero is the Java interface. You can think of an interface as a strict blueprint, or even better, an ironclad contract. Unlike a standard class, an interface typically contains abstract methods. That means they are just declarations of an action without any actual body of code attached. A class adopts this blueprint not by extending it, but by using the implements keyword, which effectively signs a contract saying, yes, I will perform these actions.
And here is exactly why this is such a game changer. Because the methods in an interface are implicitly public and abstract, meaning, again, they lack a method body, the implementing child class absolutely must write the body itself. Since there's no predefined method body coming from the parent, this brilliantly bypasses the diamond problem. Even if you implement multiple interfaces that demand the exact same method, there is zero ambiguity. Why? Because there's only one implementation body, the one you write directly in the child class. This is the secret to safely allowing multiple and hybrid inheritance in Java.
All right, Section 5, Classes versus Interfaces. Let's set up the ultimate showdown and directly compare these two fundamental architectural tools so you know exactly when to deploy each one.
The absolutely crucial point here is understanding the relationship type. Class inheritance represents a strict is-a relationship, right? A dog is an animal. It contains strict method bodies and creates somewhat rigid family trees. Interfaces, on the other hand, represent a contract or a capability. A dog might implement a playful interface. It's much more about what the object can actually do. Containing only abstract methods enables massive scalability and cross-pollination across completely different types of objects.
When you compare these features side by side, it cements exactly when and why you choose one over the other. You use extends for classes and implements for interfaces. Classes don't support multiple inheritance. Interfaces absolutely do. Classes have actual method bodies, while interfaces are abstract only. And regarding constructors, well, classes inherit the setup process via the super keyword, while interfaces don't have constructors at all, simply because you can't instantiate them as standalone objects.
Which leads us right into Section 6, Key Rules and Keywords. We're nearing the end of today's explainer, but before you start actually writing code, we need to rapid fire through the essential rules of engagement and the exact keywords you'll need to wield them.
Okay, let's hit these fast. Number 1, extends. This is what establishes your core parent-child class relationship. 2, implements. This is how your class officially adopts an interface's contract. 3, super. This gives you a direct line to access parent-class constructors and methods from within the child. 4, this, which points directly to the current class object you're working in. And 5, @override, an absolutely critical tag that tells Java, and honestly other developers, that you are providing a specialized child implementation of a parent's method.
Now, I want to drill down into a very specific rule regarding those constructors. While normal methods are inherited, constructors themselves are actually not. But don't worry, Java has a built-in safety mechanism here. Even if you don't write it out yourself, the child class automatically and implicitly calls super for you behind the scenes. It does this just to make sure that the parent's structural foundation is fully initialized before the child is built on top of it. Pretty smart, right?
And that brings us to our core takeaway for today's explainer. Inheritance builds your foundation, but interfaces unlock your scale. You now have the exact blueprints you need to avoid the diamond problem and build truly robust software. So, I want to leave you with this provocative final thought. When you sit down to architect your very next Java application, are you going to be stuck building rigid family trees? Or will you design flexible, scalable contracts? The choice is entirely yours. Thanks so much for joining me on this explainer, and